I was going to start by thanking you for spending such a clear night inside with me, but that diagonal band of clouds from the northwest seemed like a dig at me because I am also from the northwest as well, so I felt like, was that my fault? But anyway, thank you for spending your Wednesday evening to talk about my personal favourite topic of supermassive black holes. And in particular today, what I want to do is try and challenge some of the common misconceptions that you might have about black holes and convince you that it is not actually easy to grow a black hole. And that statement often throws people just a little bit because people seem to have this picture in their head of black holes as just kind of like an endless hoover, right? Just hoovering anything and everything up around it. But that is not what black holes are like at all. I want you to get rid of this idea that black holes are hoovers. I want you to banish little Henry there from your mind. And instead, I want you to think of black holes as a bit more like couch cushions. Your settee in your living room, right? It's unassuming. It's sat there happily. Nothing is being sucked towards it. But if you lose something down the side of there, right, it is gone for good. So let me explain what I mean by that. To understand essentially why black holes are black, we have to understand something called escape velocity. Escape velocity is the reason why if I or any of us in this room jump, we come back down to, thank you, that was beautifully demonstrated. We come back down to Earth, right? Because I can't jump with enough energy to lift me up at a speed greater than the Earth's escape velocity, which is 11 kilometers a second or 24,000 miles per hour. The only thing that can are rockets, right? We give them enough energy to either make it to Earth's orbit or to escape Earth entirely and make it to the far edges of the solar system. And the key thing about escape velocity is that the further you get from the Earth's surface, the escape velocity drops, and you don't need as much energy to resist that pull of gravity from Earth anymore because you're getting further away from it all the time. A black hole is black because its escape velocity is faster than the speed of light at 299,792 kilometers a second. That's 27,000 times bigger than Earth's escape velocity. It's huge. It is, quite literally, the fastest speed there is. Nothing can travel faster than the speed of light. That's what Einstein's theory of special relativity tells us. So nothing can escape a black hole, at least only when it gets too close to it. Like I said with Earth, the further away you are, the escape velocity drops, and it's the same for black holes. It's only when you get too close can you not escape. I'm gonna have to get rid of this awesome video now. I'm so sorry because it is just mesmerizing. This is why I always choose a window seat on an airplane, because you never know, there might be a rocket launch out the window. So to understand this idea of getting too close to a black hole, we need to understand how a black hole is formed. And I think this is our common sort of first misconception, right? Black holes are not holes. The name kind of lies to you, right? People picture sort of this like nothingness or a hole in space that you just fall into like a well and get stuck down. But I think a better name for a black hole would be dark star, because black holes are formed from stars, specifically dead ones. Now, technically, I could have a black hole of any mass, right? Any weight, size, whatever you want to call it. I could take my phone right now and squish it down so that all the space between all the atoms disappears, and keep squishing it and squishing it and squishing it until it became so dense and compact that it was compressed into a tiny little speck. It would eventually, at a certain point, have a pull of gravity so strong that not even light can escape. And we call that point the event horizon. Now, it's not a point, it's a sphere, right? Because you started with something that was three-dimensional and you squished it down, and you've ended up with something that's still squished down into a very, very small point, and then it gets this sphere around it at that, and that's the mark where it says, right, you'd have to be traveling faster than the speed of light to escape this thing that you've squashed down. It's like a surface, like the Earth's surface. And it's that surface that you'd have to be going the escape velocity, the speed of light to escape it. So yeah, okay, behind me, I'm showing it in 2 dimensions, but we have to remember this is 3 dimensions, right? Now, if you're thinking, Becky, that sounds like a terrible idea, do not take your phone and squish it down into a black hole. We'd all be sucked in with it if you did that. No, we wouldn't, because black holes aren't hoovers, right? So none of you would be getting hoovered up by my iPhone black hole. Because it'd be also the same mass as my iPhone is now. It'd be the same, amount of stuff there. So the amount of gravitational pull I feel between me and my phone now would be the same if it was a black hole. I'm not getting sucked towards the phone now. Oh, there's the alarm gone off. It was quite ominous in the background. It was making me feel like I had to really speak quickly. And we can actually work out, okay, if I did this to my phone, I squished it down into a black hole, what would be the size of the black hole I'd get? So the size of this event horizon, this sphere where inside everything would be trapped because you'd have to be traveling faster than the speed of light. And you can actually work it out. I remember when I was sat at university in a lecture theatre just like this, and we were sort of learning about black holes, and the lecturer put up the equation that was like, here's the equation to work out, how big a black hole would be if you had this certain amount of mass. And I was like, great, let me work out how big of a black hole I would be based on how much I weigh. And that was the first thing I did. But now we can do it with this iPhone as well. A 1.9 kilogram iPhone 13, which is what this is, you plug it into a fairly simple equation. You get out that the size of the event horizon that it would have would be, and I'm going to take a very big deep breath here, 3 meters. That is 27 zeros, ladies and gentlemen. It's tiny. It is a quintillionth of the size of an atom. Only at that point would light not be able to escape the black hole of my iPhone. And you can work out, right, a human legging it at, let's make it a nice round number of 20 miles an hour and assume we're all Usain Bolt. You would be able to escape it at a distance of 0.3 picometers away, which is, 0.3 trillionths of a meter away. So we'd all be fine. So if I could, I'd gladly take my phone and I'd squish it down into a black hole, because we'd all be fine. I mean, I don't think I can. My noodle arms definitely aren't strong enough to do that, unfortunately. There's only actually one process that we know of, that we've got observational evidence that we've seen in the universe that it can actually make a black hole, and that is a supernova. So a star's life is a constant fight, right? You've got gravity crushing down on it all the time, and then you've got these nuclear reactions in the middle where the star's taking hydrogen and fusing it together to make helium, and that gives out energy that then pushes outwards on gravity, crushing inwards. But it's a constant fight. So as soon as the star in the center, in its core, where it's hot enough and dense enough for those reactions to take place, as soon as all that fuel runs out, you lose the thing in the middle that's resisting gravity. And so gravity starts to win. The star shrinks in on itself before going supernova. So all the outer layers rebound off the dense core and get thrown outwards. We call these beautiful nebulae that we see. The very core of the star is what then starts to collapse. What's left behind depends on what kind of star you started with in the first place. So if you actually start with something like the sun, at the end of its life, won't make a black hole, sadly. I'm sorry to disappoint all of you who were hoping that the sun would become a black hole one day. It will actually give us what's known as a white dwarf. What's happened there is that gravity has taken all of that helium that's been left behind in the core after all the fuel, the hydrogens ran out to fuse it together to make all that helium, crushed all of the space of those atoms out, and you've just been left with the particles that make up the atoms. So protons and electrons, just all buzzing around each other. And that buzzing around is essentially now what resists the crush of gravity down. You can't force those protons and electrons together until you've got more gravity crushing down. So, okay, what if we added more mass to that white dwarf? Or if we started with a bigger star than the sun in the first place? then gravity would have enough strength to literally force those electrons to merge together with protons to become another type of particle called neutrons. And then all of a sudden, the thing that you've got resisting the crush of gravity down is just neutrons arrayed as tightly as they can go, like some big neutron crystal. What if you start with an even bigger star than that? What happens to the core of the star then? Well, we don't know. Because you crush that material so much that you form an event horizon, this sphere of unknowingness around it where you no longer get any light coming from it. If there's no light, there's no information that we can get about whatever's in there. It could be some weird form of matter that we've never seen before. There is this sort of next stage of like what's happening to the particles in these atoms. Some exotic, weird stuff that we've never seen. Or it could be what the maths tells us, that everything just gets squished down into an infinitely dense, infinitely small point that we call a singularity. We just don't know because we can't get any information from it. And this is one of the things that if you are a scientist that studies black holes, you kind of have to come to terms with. The fact that you will never know, and as your life of a scientist, ask questions and find out things, but just from the laws of physics as we understand them, we will always have that question mark. It's really annoying. So this is why I like to say that black holes probably should be called dark stars. Shouldn't picture them as holes, shouldn't picture them as hoovers. They're just sort of like the next stage of the evolution of stars. You know, if we were going to make a Pokemon reference, this is the time that we would do it. I'm a millennial, so I was going to do it at some point, right? But I like to think of them as this next stage of the evolution, right? If you just keep adding more and more stuff to these dead stars, eventually you're going to make a dark star, aka a black hole. So now, I hope we understand black holes a little bit better. There's one more misconception I want to get rid of out of your brain, and it's the fact that we can't see black holes. We can, technically. They're not really black at all. Okay, yes, we can't get light from the event horizon. That question mark is always still going to be there. But actually, black holes are some of the brightest objects in the entire universe. We can tell that black holes are there because of what they do to the stuff around them. The stuff that does get just close enough to actually get heated up so it becomes incredibly bright. This is how we see the majority of black holes and know that they're there. Maybe you've got a nearby star that is close enough so that the black hole can start drawing in material around it. It gets sped up to huge, huge speeds, it then heats up due to friction, and it starts to glow in things like UV light and X-ray light so that we can see it. They are whoppingly bright when they do this. And so if you actually look at the night sky, not in visible light like we see with our eyes, but in X-ray light, so much more energetic light, it's got a very, very high frequency, you can actually see where the black holes are. So what you're looking at here is the entire night sky, but it's been projected down onto a flat surface, right? So you've taken the inside of a sphere and squished it down. I don't know if you've ever tried to like peel an orange in one go and then see what you're left over with the peel, but if you try and flatten it down, it's not making a nice, perfect shape, right? And so if you take the inside of a sphere and flatten it down, you get this kind of like oval shape. So that's what you're seeing here. And every single dot is not a star, but a growing black hole. Might be some neutron stars in there, but mostly they're glowing black holes. Now what you've got in the center, running all the way through the middle there, you can see there's probably a slight concentration of them. That's actually the black holes in our galaxy, the Milky Way. Milky Way is kind of like a flat, like frisbee shape. So you're seeing the frisbee shape on its side, where all the stars are, and where all the stars that make black holes are, so you end up with a lot of black holes in that middle bit. That's where things have gone supernova and form those black holes. There'll be other ones from our galaxy dotted around in the rest of the image, but mostly off that central bit, the dots that you can see there are not black holes in our own galaxy, but they're supermassive black holes at the centers of incredibly distant galaxies. Things like this. You might remember this image from when it was released about 5 years ago now, dubbed the big orange donut by most of the press, right? It was the first ever image of a black hole that we got. It is, what you're seeing is radio light, so this time less energetic light, big long sort of lazy wavelength kind of light. Radio light from the material that's spiraling around the black hole itself. And this one is the supermassive black hole at the center of the galaxy Messier 87. It is 6.5 billion times heavier than the sun. And the entire solar system could fit inside of it. So we've gone from like 27 zeros of the size of an iPhone black hole to you could fit the solar system in the event horizon of this one. And again, the reason we know it's there is because the material spiraling around it gets accelerated to huge speeds by the gravity of the black hole, superheated so it glows. Enough so that we can see this despite the fact that it's 50 million light years away. Take light 50 million years to get to us from it. But how does the black hole grow that big? If you remember, I told you there's only one process that we know of that forms a black hole, and it's when a star dies. And when that happens, you make a black hole that's kind of the same mass of stars. So anywhere from, say, 3-ish times the mass of the sun, so 3 times heavier than the sun, up to maybe 100 times heavier than the sun, if we're really pushing things. Supermassive black holes that we find at the centers of galaxies, though, are anywhere from 1 million times heavier than the sun to tens of billions of times heavier than the sun. So how do you do this, right? Like, we kind of need another Pokemon past Raichu, right? We just need to dig the next evolutionary stage. We need to add more mass, just like before. We need to add more stuff in there so that it grows, so that the dark star gets bigger and heavier and heavier. The problem is that's really difficult. It's not easy growing a black hole, especially by that tremendous amount. You know, where are you going to find 1 million suns from, right? And the reason why it's so difficult is because we have to remember that most stuff likes to orbit other stuff, right? So in the solar system, for example, right? Planets, asteroids, comets, all the random detritus of the solar system orbits the sun. And again, if I could take the sun and collapse it down and squish it and make it into a black hole, why not? Because it would be the same size, like the same mass, the same amount of stuff in there, so it would have the same pull of gravity, and none of the planets would even notice, really. They'd be like, yep, still getting the same pull of gravity from the sun, it just happens to now be a black hole, so off I'll carry on all my orbits. Nothing would change the orbits of the planets. They're on very happy, very stable orbits. You would somehow have to take energy away from a planet, so let's say Earth, because we're on it now. Let's take away energy from the Earth, or even give Earth some extra energy to change its orbit around the sun. You're not going to do that if you have some massive collision or something like that. Maybe then you could change its orbit. But even if you turn the sun into a black hole, the Earth is not going to start getting sucked into this new black hole sun because black holes aren't hoovers, right? Everything will happily just orbit it. And in the same way, stars will happily orbit the center of a galaxy, which is where we find the supermassive black holes. So this is a series of images, like a time lapse. You'll see there's the year ticking by over here in this corner, right? There's many, many images of the very center of our galaxy, the Milky Way. And what you're seeing there is the stars in the very center. And we're basically tracking the movements of those stars over what, maybe like 2 decades, 15 years, something like that. And what you can see, one of them eventually gets a little sort of circle. There you go, that one. Watch that one. And you'll see it loop around and do one full orbit of the middle of the Milky Way. There you go, there's its orbit drawn on and everything. That's a very fast-moving star to do one full orbit of the Milky Way in 12 years. It's actually the star closest to the very center. And from the movements of all these stars, you can work out, okay, if this one's moving this fast at this amount and this one's doing that, you can work out how big the thing is that they're orbiting around in the middle, how massive it is, how heavy it is. And when you do that, you find that it's an object that we can't see, there's no light coming from it, that's 4 million times the mass of the sun, It could fit inside Mercury's orbit. So 4 million suns inside of Mercury's orbit. The only thing that can be is a supermassive black hole. And that work actually won Andrea Getz in the Nobel Prize a few years ago, if any of you remember that announcement as well, measuring that mass. So all the stars in our galaxy that are orbiting around the supermassive black hole in the center, including the sun, because we're out there on a spiral arm somewhere. This is not the Milky Way, by the way, because we're in it. So we can't go out of it and take a picture. This is another galaxy that sort of looks like the Milky Way, what we think the Milky Way looks like. But all of us, hundreds of billions of stars, happily orbiting the black hole in the middle, not getting hoovered in at all. Okay, so you're not going to get your mass that's going to grow your black hole from stars. Fine. But can you see when you look at this image that there's also sort of all the fuzzy sort of stuff in between the stars as well? That's sort of glowing ever so slightly. That's gas in a galaxy, hydrogen gas, that you could make more stars from as well. But also, there's a huge amount there. You could use that to grow your black hole. The problem is, gas is also just happily orbiting the very center of the galaxy. It's going to stay there unless somehow you take energy away from that gas, or you give the gas a boost of energy. Then you can maybe change the orbits of that gas. And then maybe, just maybe, you might be able to send some tumbling towards the center of your galaxy so it can actually get hoovered or eaten by the black hole and grow the black hole in mass. Okay, how do we do that then? How do you somehow take gas that's on a nice happy orbit and somehow take energy away from it so that it can grow the black hole? What processes could possibly do that? What about a merger of two galaxies that creates a whole load of chaos? So this is actually the fate of the Milky Way in a few billion years, no reason to panic, with its nearest neighbor, Andromeda. You can see Andromeda in the night sky as well from the northern hemisphere, so hopefully maybe one night when it isn't cloudy, when the talk finishes, you could try and go see that. But in a few billion years, they're expected to collide and merge together and become one galaxy. And no two stars will collide in that process because the space between stars is big enough to lower that probability. But hopefully what you'll see is that the sort of forces of gravity essentially end up like scrambling things up and shifting things around. So that actually a lot of, not just the gas, but also the stars get sent to the center. You have this big blob now. You've got rid of all those beautiful spiral arms in the Milky Way, and you've ended up with one big blob that's known as an elliptical galaxy. Blob is not exactly a scientific term, but I like it. But this is what we think will end up happening, is that not only will you change the shape in stars, but also you'll scramble up that gas and send some of it tumbling towards the center to hopefully get eaten by the black hole. That's actually what happens if you merge together two galaxies that maybe have around about the same mass. If instead you merge the Milky Way with that little thing up there, you see it in the top right? That's the Triangulum galaxy that's showing in this simulation. If you dropped that into the Milky Way, it'd be more like sort of dropping a stone into a pond, right? You get all the ripples outwards that would definitely shake things up, but it wouldn't be as drastic of a change as this. What you'd end up doing is the Milky Way would maybe keep its nice spiral arm structure on the edges, but in the middle, you'd probably form one of these things, like a mini blob, right? You can picture it kind of like two fried eggs back to back, right? You've got the nice white bit is your spiral arms on the edge, and then you've got like a big blob of stars and gas in the middle that we call the bulge. And we see this sort of merger of galaxies happening wherever we look in the universe, right? We can't actually watch it playing out because the whole process takes billions of years, but we can look in one direction and see galaxies that are in one stage of a merger getting closer, and we look in another direction, oh, there's some more galaxies that are a lot closer together still in this whole merger stage, and oh, look, there's some that look like they've just merged. And so from simulations and our observations of the universe, we piece together like what's going on in terms of like mergers and what effects they have of changing the shape of galaxies to give you this big blob of stars in the middle instead of a nice spiral shape. Maybe even growing the supermassive black hole. Because, ladies and gentlemen, are you ready for the first graph of the talk? This is where this idea comes from. All right. On the x-axis here, we have the mass of the egg yolk, right? In our fried egg of a galaxy, we have the mass of the blob of stars you form in the middle, right? Of a galaxy, the bulge. And on the y-axis, you have the mass of the supermassive black hole that you find in the center. And hopefully, oh, hang on, I should also explain, this is what's called log units. So basically, the little number next to the 10 means how many zeros do you have after the 1. So 10 to the power of 9 means 1 billion, 1 with 9 zeros, and 10 to the 12, 1 with 12 zeros, 1 trillion times the mass of the sun. That's what that means. And hopefully what you can see is that when you make this graph and you put down all the galaxies, you have a nice correlation between the two, right? Basically, the heavier your galaxy's little blob of stars is in the middle of it, the heavier the black hole is. We say that the two co-evolve. You grow one, you grow the other, right? You grow them together. And the thing is, this bulge of stars we know gets grown if you have a merger. You have a giant chaotic merger of two galaxies the same mass, you make something that's entirely a blob. And if you have something that's, you know, just like a little ripple into a pond of a smaller galaxy, you make just a little blob in the center. But either way, we think that the blobs, the bulges, are grown by mergers. So if these two things correlate, great. Black holes must grow in mergers. It must be mergers of two galaxies that are scrambling up all the gas and send it tumbling towards the center to grow the supermassive black hole. Great. Problem solved. That's how supermassive black holes grow. The problem is with that whole nice, neat little picture is that not all galaxies have had a merger. The Milky Way, for example, doesn't really have that much of a blob in the center. So how does it have a supermassive black hole then? There must be some other process that can do this. Basically, what my science question asks is, what about these things, right? Here's the ones I was just talking about. This is Andromeda, right? It's a very, very good description, very good example of two fried eggs back to back stuck together, right? You can very clearly see the outside, the spiral arms, the egg white, and that big blob of stars in the center, which we call the bulge, which is the egg yolk. And then on this side, you've got something that's basically entirely just spiral arms. There's no blob in the center. This is essentially like the egg white omelet of the galaxy world, right? There's no yolk there at all. And so my science question is, well, what about the black holes in those things? How big are they? How supermassive are they? We know the Milky Way's black hole is 4 million times the mass of the sun, and it's not really had a merger in 10, 11, 12 billion years, the Milky Way astronomers think. So how did it grow so big? And do we know that these don't have supermassive black holes, or do they have supermassive black holes? We just don't know. Someone's got to go and find out. This is my research topic, right? And the first thing you got to do if you want to go study these things is you got to go find a load of them. So that was the first job. And specifically, you don't just want any nice, beautiful spiral galaxy that's been left alone and has never had a merger. You want things with a growing supermassive black hole. So ones that are taking in material, letting it, get superheated so that it glows so that we can see it, so that we know that it's there. And we actually have a hope of figuring out how big is the black hole. We'll get to that. Now, what we did was start with a sample of galaxies, a big survey that had been done of the night sky to be like, yep, there's a galaxy there, there's a galaxy there, there's a galaxy there. We started with those, which is about 1 million of them, and we said, let's find all the things that don't have blobs of stars in the center, they don't have the bulges, and they have a growing supermassive black hole, and let's make a sample of them. And from 1 million, we found these 100. It's actually 101, but it fell off and it didn't look as neat on the slide if I included the 101. We found these galaxies. So they're incredibly rare that you find a galaxy that has both a growing supermassive black hole and also has never had a merger. Now, you might be looking at these things and go, but Becky, there are giant, big, bright blobs in the center of these things. What are you talking about? But can you see how the bright spots in the center often have a slightly different color? They're sort of purplish, right? As opposed to the bluey or the yellowy starlight around them. What you're seeing there is the light from that glowing material around the supermassive black hole. It's pushing into that purple region because it's like UV light that you're seeing. It's very energetic. So that's kind of how you know that the black hole is there in the first place. And okay, you could be hiding a bulge, a blob of stars underneath that. But for the most part, we're pretty sure these are spiral galaxies that have not had a merger, at least from these images that are taken from the ground that are a little bit fuzzy, fine. But let's just go and check, shall we? Let's go check with, like, say, the Hubble Space Telescope that can get us like big, beautiful images like this and show us, yeah, this is a galaxy that does not have a big bulge of stars in the middle. You've just got that bright point of light in the center that comes from the supermassive black hole, but otherwise never had a merger. Great. So now you've got 100 things that you think they've never had a merger. Now I want to know how big the black hole is in the middle, right? How do you work that out? Because what you want to do is put them on that graph, right? That first graph that we saw before, and check where do they lie? Do they lie like way off down the corner and on the correlation still, but yeah, they're super tiny, or do they break that correlation somehow? So to do that, some poor soul has to go to the telescopes in far-flung places in the world. In this case, it was La Palma in the Canary Islands. And I was so sad to have to make this trip, but somebody has got to do it. So this was the start of my work day at sunset, because if you're an astronomer, you work nights, right? If you're using telescopes. And you can see the sun setting behind me. We're high up a mountain to get up above sort of, water vapor that's in the air that's going to ruin your observations and make everything a bit fuzzy. Twinkle, twinkle, little star is literally an astronomer's worst nightmare. You don't want anything twinkling. You want it nice and steady and stable. You can also see there's clouds in the background behind me. I'm above the clouds. That's very helpful as an astronomer as well, as we've learnt this evening. But also you can see telescopes behind me that are opening up for the night, right? So you have this big, beautiful dome structure, this sort of like hemisphere kind of thing that houses the telescopes. And you see the one up here on the left-hand side is sort of opened, this sort of little slit basically, so that the telescope can poke out, and then wherever you want to point the telescope, you rotate the whole dome with it. Or you can do what the Liverpool telescope decides to do, which is kind of like a Pac-Man style of opening, which I also quite like. There's some great pictures of the moon like lining up with that perfectly, and it really does look like Pac-Man. And we were using, when we went to do this, the Isaac Newton telescope, which is a UK-owned telescope. The telescope inside that big dome is 2.5 meters across. So what do you reckon this is? Like maybe 1.5 meters, so you get another meter again off the side of it. That's the size of your telescope that's inside there collecting the light. And just to give you a sense of scale, the building that it's sat on is a 4-story building. It was built in the 1970s, and it was built so big because it was the only telescope on the mountain at the time. So they had to build things like, dormitories and bathrooms and kitchens and libraries so the astronomers could work in there as well and things like that. It was the living quarters for anyone who was using the telescope. Since then, there's been a lot more telescopes built on the site. They've actually built like a centralized, almost like little hotel kind of situation to put all the astronomers up. You get your dinner cooked for you. It's great. Actually, the best thing is breakfast when you've finished a night of observing, but they cook all that for you and it's wonderful. But it also means that this building is now practically abandoned as a 1970s time capsule. In the day, it's wonderful. At nighttime, it's terrifying. Especially because when you're observing in the control room up there, and that sort of little thing that boops out, your bathrooms are in the 1970s abandoned building. You can't turn on any lights because, God forbid, a light escapes that's going to ruin your observations. So you're literally walking through a pitch black abandoned 1970s building. And it's like you can hear the cinema's worth of people just screaming at you to turn on a light. But it's okay. I went through the fear and got data, which is what I all went for in the first place, right? That's why we do it. So what data were we trying to get? Like I said, we had this sample of black holes that were glowing, right? And the stuff that was glowing is the hydrogen gas that's spiraling around the black hole. Hydrogen, the most common thing in the universe, is what makes up stars. You could make stars out of that gas, but as we just heard, it tumbles towards the center and it ends up growing the black hole. So we were trying to observe this glowing hydrogen, all right? So to understand what we see when we look at hydrogen, we need a chemistry lesson. I know, I'm so sorry, you signed up for a physics talk and I'm giving you chemistry, how dare I? So a quick refresh, or a quick lesson for those who've never come across it before. You have a hydrogen atom, it's the simplest thing you can have. One proton orbited by an electron. If you shine some energy, some light onto that proton, you essentially can give the electron energy. So it's like, I don't want to orbit the proton here. Oh, I'm going to jump and I'm going to orbit the proton up here instead. In the next place that I'm allowed to, that makes this sort of, like perfect circle, that have enough energy to do that. But it's all supposed to be there, and eventually, electron will give that energy back out and drop back down. And it gives that energy out as light. Now, quantum mechanics tells us there are only certain places that an electron can orbit a proton. And they have the exact same energy levels every single time. So every time that electron makes that drop back down, it has to give out the amount of energy that separates them, which is always exactly the same. So it's always the exact same energy that's given out as light. And when you give out the same sort of like energy light, it's always the exact same wavelength or color. Always the exact same color. So if you take light from the center of your galaxy and you split it through a prism, Pink Floyd Dark Side of the Moon style, you will get a trace of how much light at each color you get, right, in your rainbow of light from that galaxy. And you will get a peak, a bright, sharp peak for all that hydrogen gas that is glowing near the black hole. It will be this big, sharp, sort of stalagmite, whichever way around. You could just turn it upside down, it'd be the same. It would look like this, essentially, right? Here's our second graph of the talk. If you've got wavelength of light on the x-axis, so your color of your light here, and on your y-axis, you've got the amount of light that you get, and you have all this hydrogen in the center of your galaxy giving out light, that's what you should expect to get, this big, bright spike of light at that color. That's not what we see, though. It'd be nice if it was that, but it's not. Instead, we see this. The white line is real data taken from that Isaac Newton telescope that I showed you before of the hydrogen gas that is spiraling around the black hole. The blue cyane line is a fit to that data, and then the red one, I've just like shifted it down so that you can see the shape better. It's not a super tight, sharp peak. It's been like smeared out. What's going on here? People who've been like paying attention, you keep saying this gas is spiraling around the black hole. That means it's moving. That means some of it is coming towards you and some of it is moving away from you. So it's getting Doppler shifted. You're familiar with this idea of Doppler shift, right? When you hear like an ambulance siren, or if you're stood on a motorway bridge and you've got cars coming towards you and then away from you. The sound that you hear when they do that changes. So say it's an ambulance coming towards you and it's giving off that siren noise and wee, wee, yeah, you guys can do it. As it comes towards you, it gives off that sound wave, but as the ambulance moves, it squishes the sound wave, right? And if you squish a sound wave, you get a higher pitch. Then as the ambulance moves away from you, you stretch out the sound wave as it comes towards you and it gets stretched down to a lower pitch. And that's what you hear, right? It kind of goes like, woo, yeah? Same thing can happen to light. Sound wave, light wave, both waves, same thing can happen. And so as the gas comes towards you and emits that nice big bright spike of light, it gets squashed, goes to a bluer, shorter wavelength and gets smeared out over this side. And as it moves away from you, as it spirals around the black hole, it gets stretched out to a longer, redder color of light, and it gets smeared out to this side. And the really cool thing about this is that because we can see this smearing, we can measure how much the light is shifted by, therefore know how fast it's moving, and work out how big the thing is that it's moving around. If you can measure how wide that thing is, you can measure the mass of a supermassive black hole. Which is insanely cool. Like, can we take a minute to appreciate how cool that is? Like, it gives me sort of like, you know, when I was doing this, and I was just like, this is incredible that I can do this as a job and someone will pay me. How did I pull this off? But like, as humans, the fact that we have figured out how to do this, like, think about how many things we had to go through, like I said, to reach this point. First of all, we had to work out that black holes existed and that they were at the center of galaxies and that they could grow supermassive. But we also needed to know some chemistry and some quantum mechanics. And all the engineers had to figure out how to build a telescope and how to split the light and how to record that accurately enough so that we could do so many areas of science, right? Literally had to come together to make that incredibly, what is almost like a simple measurement at the end of the day, just measuring how wide that thing is, to measure the mass of a supermassive black hole. Looking at this, it is the literal sort of embodiment of standing on the shoulders of giants, to me. There are so many things that have to come together to make that possible. It's incredible. It blows my mind. It blows my mind. But back to graphs. I mean, we're already on a graph, but back to another graph. Remember this one from before. This is the thing that motivated the whole research, right? We said that this meant that mergers grew supermassive black holes because you have a correlation between the amount of bulgy, blobby thing in the center that's grown by mergers and the black hole. And what we wanted to do was go away and measure the supermassive black holes with that telescope we just saw in the center of galaxies that have never had a merger and see where they are on this plot. Let's do that then. Let's add the points. There they are. I was going to get you to drum roll, but I thought that was too dramatic. Now, you're probably a little bit confused because you're like, well, why are they all arrows, for one thing, and why are they all pointing this way? There's something called upper limits. So do you remember before I showed you those images and I was like, you probably like, they have bulges. There's these big blobs in the center. And I was like, no, that's the black hole light, right, that you could see. You could technically hide a bulge under there, right? And so you have to model for that. And you say, okay, well, if you could hide a bulge of stars under there, what's the maximum amount of like mass in that bulge, you know, heaviness in that bulge that you could hide? And basically that's where the end of the arrow starts. And you're basically saying, but it's probably over here somewhere, right? If we could technically measure it, but we can't. And if we were going to fit a line to that, it's probably over here somewhere, right? And this sort of like dicky bow shaped thing, that's the sort of correlation line that you draw. Which I hope shows you how incredibly weird these galaxies are. First of all, if you just go straight up to the highest arrow up there, that is a black hole in the center of a galaxy that has never had a merger. It has a black hole of 1 billion times heavier than the sun? What? If the only way to grow supermassive black holes is through galaxy mergers, how did that get so big? That doesn't make any sense. None of those points on there, those arrows, make any sense under that way we think that black holes grow. It would be nice to know where exactly they are on this plot, but with observations we can't get that. But thankfully, it's not just observers that use telescopes that work as astrophysicists. There's people who like to code things on computers and basically try and simulate the entire universe that just work down the hall from you. And you can be like, hi, have you looked at this in your simulations? And they go, yeah, sure, here's the data points. And you go, great, I can put them on this plot, at least in simulations. And it's almost like you can see where the arrows are all actually going to shift to if we could measure that. And you can see they're so much bigger than you would ever think given this correlation. So what's going on here? Well, the fun thing is with simulations, you can like rewind time. You can do all sorts that you can't do with observations, right? You can be like, tell me what was going on like 10 million years ago. And let's track, how did the black holes grow? Where did all the stuff come from that's in black holes today? How did it get there? How much of it came from galaxy mergers? And so if you do that, you get this plot, right? I don't know why we're going to blame the fact that they're simulators, but today's on this side of the plot. This is now, and then you're going back in time this way. I know, they're strange people. But that's time, okay? And then on the y-axis, you have how much stuff is in black holes, how much they've grown cumulatively. And the red line there is the stuff that's gotten into black holes from mergers. And if you go from the early universe and you go all the way up to today and you follow that red line up, you get to 35% of all the stuff in black holes got there because a big merger came and scrambled all the gas up and sent it tumbling towards the center. Everything else is not mergers. So what is it? Essentially, that's my research question now. We went away, we measured the masses, we showed, oh, actually, these are weird and this breaks things, and oh no, it broke things. Actually, that's kind of good because now we've got more science questions to ask, like, well, what is growing them then? And we've got to figure that out. The problem is I don't know yet. I'm still working on it. That's the whole fun bit of research. Fun bit of research, you know, is not knowing and trying to figure these things out. Maybe I'll have to come back in a few years' time to give another talk to try and let you know what I've been up to. And then hopefully we can find out together what actually is then growing supermassive black holes. So, how do black holes grow? They're not hoovers. If that is one thing that you take from this entire talk tonight, it's this that I want you to remember, okay? That they are not hoovers. We are not about to fall into one. We are okay. Sometimes it seems like supermassive black holes get that big because of two galaxies merging together. That was how we thought that all supermassive black holes grow, or used to. But now we think that that's only 35% of the time. And 65% of the time, it's something else. There's something else that we're working on, is that perhaps just the existence of spiral arms, they act like a funnel. And as they move around the galaxy and drag things around, they send stuff towards the center. Or maybe it's that the galaxy can actually take in material from what we call the cosmic web. There's this big gas web that connects everything together, all the galaxies together in the universe. Perhaps because they're so isolated and left alone and calm, everything can sort of trickle in towards the center that way. Maybe it's even something called a bar in a galaxy, where sometimes the spiral arms don't go to the center, but they connect to this big long structure in the middle that then could also funnel gas. We're working on figuring it out. But if there's one thing, apart from the Hoover, apart from Henry Hoover, that I want you to remember from this talk today, it's that black holes, yep, they aren't endless Hoovers, but they're more like couch cushions. Thank you very much.
Amazing. I think I'm going to remember that black holes are couch cushions. Do we have any questions for Becky? Oh, someone be first. Great. Yes.
Oh, nice jumper.
Yes.
Yeah.
Do we believe there's any possibility of a link between dark energy and dark matter that's influencing
Black holes.
black holes?
So there's a couple of hypotheses. First of all, that black holes could be dark matter. So dark matter, this stuff that we know is there because we can see the effect of its gravity, but it doesn't interact with light in any way. That could be black holes. Now, it can't be the black holes that are formed from supernova. There's just not enough supernova going on throughout the lifetime of the universe to account for it. What people think it might be is something called a primordial black hole. The problem is we also don't have any evidence for those existing. That's another one of those like, oh, we could form a black hole this way, and the maths suggests this. In the very early days of the universe, you could essentially have like matter that just clumps together that gets dense enough to collapse into a black hole. But again, we've no evidence that they exist. And there's a couple of things that like people still need to work on, like making the numbers match in terms of like black holes being dark matter. There's also an idea that black holes could be dark energy, which is the name that we give to the thing that is causing the universe to accelerate in its expansion. That one, I really, really, really doubt. People work through the maths, and it's such complicated cosmological maths that I just sort of get to the end of it and go, I'll take your word for it. But then the observational evidence that they've used to prove that, I'm like, I just don't think we understand how black holes grow. Like, I think a lot of their arguments stem on the fact that a lot of the stuff growing black holes is by mergers. So there's two sort of ways that you can connect to them, but they are very much hypotheses and ideas that are still sort of being considered rather than like fleshed out theories.
Thank you.
Yeah.
What do the things that go into black holes end up?
In the black hole forever and ever. They never make it out is the thing. So do you remember that picture I had before where there was the big question mark that we didn't know what happened at the end just before we got to the Pokemon? The question mark is basically like, we don't know. We think it gets trapped there forever because we can see the fact that it's heavy. So if material's gone in and it's still very, very heavy, then the material still has to be there somehow. There are some people, though, that like to stand with chalk in front of chalkboards and write lots of equations down, who think that maybe it does pop out somewhere else. Maybe in another universe entirely, it's something called a white hole, which is like the opposite of a black hole. So instead of like taking everything in, it like vomits everything out.
Why aren't they Hoovers like Henry?
What, the white holes or the black holes?
No, the black.
The black holes, well, they are, if you get close enough, it is a bit like a hoover. But most of the stuff is too far away for it to have an effect. That's why they're not hoovers. Yeah.
So doesn't Hawking radiation allow matter to escape slowly?
So, I love that you've asked this question, but it is also my most hated question that I could ever get asked. And the only reason is because Hawking radiation is very difficult to explain without maths. If you see the maths, you're like, yeah, that makes sense. But explaining it without maths, it's very difficult. So I'm going to try. If you will allow me, I thought I did a fairly good job in my book, A Brief History of Black Holes. There's a whole chapter on it, if you'd like. Essentially, with Hawking radiation, what Hawking said was like, black holes seem to break one of the most fundamental laws of physics that underpins our entire understanding of the entire universe. And they shouldn't do that, right? And that's that like, things should get more chaotic over time. But black holes, by sort of like putting stuff away into an event horizon and trapping that, is almost like tidying things up in the universe, right? It's like, okay, now everything's tidy, it's not chaotic. So somehow they seem to break that. And basically what Hawking said was, we don't have the maths and the theories to explain this like how he would like to. So instead he was like, I'm going to do a shortcut. And basically he was like, if you actually think of the event horizon, that surface I was talking about before, as being like a hot oven almost, because you've got all that material there that has a lot of energy, then in the quantum world, you will get spontaneous production. Yeah, this is why I said it's hard to explain. You will get essentially like random, like 2 pairs of light particles being generated, right? One of them will end up just going back into the black hole, and one could escape. And there is a chance that could happen. And this is all theory, maths, and everything on a chalkboard. It's not actually ever been observed, okay? But it's a very, very slow process when it does happen, okay? And if that's the case, supermassive black holes, like, we would almost never end up seeing any sort of like Hawking radiation from it. And even if we did, it'd be 1 particle of light. Stellar black holes, the black holes in our own galaxy that have been formed from supernovae, that are the same mass of stars, maybe we might see something from that if we get lucky. But if the primordial black holes exist, the ones that formed in the early universe, they could be much smaller. And the smaller the black hole, the more often you would get this Hawking radiation. And we might be able to see something from that in terms of radiation. It would be like gamma ray flashes, so super high energy light. Maybe even if like there's been enough time for such a small black hole to keep pushing off this Hawking radiation all the time so that it would completely lose all of its mass. Because energy equals mass times the light, speed of light squared, according to Einstein, E equals mc squared. Energy and mass are the same thing. So if you're losing energy by a particle of light escaping, you're also losing mass. Do you see now why I hate to explain this in a public setting? It's just because the maths make sense, but describing it makes it sound so sci-fi and ridiculous when you say it out loud. But it's one of those things that, like, Hawking proved it with all the maths and the theory, but we've never observed it. So we still don't know if it's a real thing or not. Yeah. You're welcome. Hi. Does a black hole ever end? Do you mean in space or in time? In space, I guess if you're falling towards a black hole and you get trapped there, then technically it never ends because that's your future forevermore. In time, we just talked about Hawking radiation and maybe black holes, if they're small enough, losing all their mass through photons escaping. Maybe then a black hole could end in that way with enough time passing, if Hawking radiation is a thing, which we don't actually know. Yeah.
Is there a limit to the amount of mass that can be in a black hole?
Ooh, great question. I love this question. I have a whole YouTube video on this if you want a big, big deep dive. But yes, we think there could be a limit to how big they can grow through the process that I was talking about, where they draw in material and they get this big disk around them that starts to glow and heat up. In a supermassive black hole, if you send stuff towards a black hole, it obviously has to form this disk, right? The gas will start to orbit the black hole. And the only way that you can then stop it orbiting and actually fall in and go towards the center is if you have collisions between particles, which lose energy and then they fall in, right? Like, sort of like snooker balls, right? You hit like the cue ball and the cue ball stops and the other one goes flying, the cue ball would get lost to the black hole, right? I'm going to get rid of that because it's very distracting right on the background. So around a supermassive black hole, you have to have that process to have it growing, right? Or you've got to like fire material like on a direct trajectory kind of like towards it, which doesn't ever really happen. You usually get it in this process. But as a black hole grows and grows and grows and grows, I like to think of them as kind of like mountains, right? A very small black hole is kind of like a really, not very tall mountain, but it's like sheer-sided, right, in terms of its gravitational pull. So you can get pretty close to it, pretty close to it, pretty close to it, and then all of a sudden it'll take you. Whereas like a supermassive black hole is like a really, like the tallest of mountains, but with a really, really shallow gradient. So you can get like pretty close to a black hole, like a supermassive black hole, and almost not realize that you've gone too far, right? But what that means in terms of its pull is that you can actually get material that's quite far away from it, that actually the pull of gravity from the supermassive black hole like is not strong enough to overcome like the pull of gravity between the molecules in like whatever clump of gas or star that you've got. And so actually it never gets close enough to the supermassive black hole to form that disk thing that we saw before that was glowing. So at some point, a black hole grows too big that it can't grow anymore. Again, that's a whole chapter in the book if you want to watch it out in the video. And we actually think there's like people work out the maths, they work out that it's somewhere between 50 to 100 billion times heavier than the sun is that limit. And we found black holes about that mass. We found one that's 68 billion times heavier than the sun. And so it could be that we're reaching the limit of how big black holes can grow like now, which is quite exciting.
Have you one last question?
Yeah, sure.
Okay.
You already had a question, so I'm sorry. You can ask that after we finish. So I'm going to go for one here instead. Oh, sorry, I was pointing to the lady behind you. Sorry, yeah, you.
Why do they call a disk and not a cloud?
Yeah, so the Earth is spinning, right? The sun is also spinning. Stars are spinning. So when stars die and become black holes are also spinning because you can't really shake a spin once you've got it, right? It's very difficult to slow a spin down. And actually kind of like like an ice skater when they're spinning around and they pull their arms in and they actually spin even faster. That's what actually happens to black holes. You take a star that's spinning at like a normal speed, collapse it down, and you get a black hole that's spinning very, very fast. So any material that comes in towards the black hole ends up spinning as well. And it's like if you take a ball of pizza dough and you set it spinning above your head to like throw it into a pizza sort of base shape, it will flatten out into that disk. It's the same thing that happens. And it's how, for example, the planets of the solar system, they all end up in that nice flat solar system plane where they're all sort of roughly in a line. And it's because whatever material formed the sun was spinning. And after the sun had formed, it then, went from a cloud to like a disk, and the planets formed from there. So it's really fun to like think about that. You can also, when you get on like a merry-go-round, or if you like hold hands with a friend and spin around and you feel that force pushing you outwards, it's basically the same thing. It pushes things outwards into a disk. Nice.
That was fantastic. Thank you so much. So we're now going to have just wait. Short refreshment break, and then back in here for a sort of planetarium show showing you what's behind the clouds. Yes, can we thank Becky again, please? Thank you so much.